All right, let's get started. Thank you everybody for coming. This week we're welcoming Tyler VanderWeele, who is not only a faculty sponsor of this workshop, but also a professor of epidemiology at the Harvard School of Public Health. And he'll be presenting work introducing e-values on sensitivity analysis.
Great. Well, thank you very much, and thank you all for coming. I'll be speaking today on this topic of sensitivity analysis, and many of us here are often working with observational data and trying to draw some sort of causal inference from that data. A constant challenge that we face is, well, might there be an unmeasured confounder, some third factor related both to our treatment or exposure of interest and the outcome. And sensitivity analysis techniques essentially try to assess how strong such an unmeasured confounder would have to affect both the treatment and the outcome to explain away our observed associations. These techniques have been around for over half a century, but are still relatively infrequently used in practice. And sort of in my own teaching, I've struggled with how do I make this more common practice, because I think this is really an important task. So about 7 years ago at the School of Public Health, I thought, well, I will start teaching this material. And one of our core courses, 80, 90 students a year, I'll force a homework assignment where they have to implement these techniques. And maybe in my discipline of epidemiology, practices will finally change. So I did this for a number of years, and it seemed like pretty much nothing happened. And so I would follow up and say, well, why aren't you doing this? I mean, you know how now, you've had to do this with the homework, and the responses I'd get back would be, well, it's kind of hard, takes some time to implement, and takes a lot of space. I mean, you have this big table of numbers, and have to explain it in the paper, and I'm only allowed 2,700 words in these biomedical journals, and then the reviewers don't understand, and the readers don't understand, so I decided it's not worth it. And I was sympathetic, at least partially, to these concerns, and then sort of started thinking about other ways where this practice of sensitivity analysis for unmeasured confounding could be more easily and more widely utilized. Sort of how do I address these objections I'm hearing from the students who had taken these courses? And that's essentially what motivated the introduction of this new metric, the e-value, a measure of sensitivity analysis, of robustness or sensitivity of our results to unmeasured confounding. So the theoretical background, which is what I'll begin with, was actually presented here in this very workshop about a year and a half ago by Peng Ding, who's now at Berkeley. And I'll be reviewing that material. I have some new additional technical results, but really the bulk of the presentation, the substance of the presentation, is how to perhaps make use of those theoretical results to make this practice of sensitivity analysis more easy to use and more common. So I'm sort of, while I'll be going through the theoretical results, I am interested in feedback on that, but also principally on sort of what you think of really trying to push this hard as an easy-to-use option to assess robustness to unmeasured confounding. So I'll go through basic ideas of sensitivity analysis. I'll talk about some of the technical results, which initially were essentially oriented on just trying to relax some of the assumptions that had been used in the literature. I'll then introduce this e-value metric, go through a few empirical examples as to how this might be used. I'll then talk about its application to other scales. We'll be focusing principally on the risk ratio scale for reasons I'll describe, but then extensions to hazards ratios, odds ratios, and continuous outcomes as well, and then make a few concluding remarks. So I introduced this metric with Peng Ding just last August in a paper of the Annals of Internal Medicine, and worked quite hard with the editors on multiple drafts to try to get this into a format which was entirely understandable by clinicians. We'll see whether that was successful or not, but the basic ideas are there in that paper. So the setting we're dealing with, we have some treatment or exposure A. We're interested in its effects on some subsequent outcome Y. We've tried to, it's observational data, we've tried to collect a bunch of measured covariate C, which we think might be related to the exposure and the outcome, but it's observational data, so we're always worried that we might have some unmeasured covariate that affects both the treatment and the outcome that might be responsible for our observed associations, conditional on the covariates. And so sensitivity analysis or bias analysis techniques are can be used essentially to assess how strong would such an unmeasured covariate have to affect both treatment and the outcome to explain away our observed association. If we're willing to speculate about the strength of those associations between the unmeasured confounder and the treatment, the unmeasured confounder and the outcome, we can also sometimes use these techniques to get a range of what we think might be plausible estimates as to what we would have obtained had we been able to adjust for that unmeasured covariate U. So an example which I'll be looking at a little later after we've gone through the results is a number of studies have found that maternal breastfeeding is subsequently associated with quite a number of maternal and child health outcomes, but it's almost all observational data. And so a concern in many of these studies is maybe we have unmeasured confounding by socioeconomic status. In the West, at least, higher SES mothers tend to breastfeed more frequently. In other studies, there's concern about confounding by maternal smoking. Not all studies on maternal breastfeeding have collected data on maternal smoking, and it turns out maternal smoking and maternal breastfeeding are quite strongly correlated with each other, so that's another potential unmeasured confounder. So to what extent from the studies that we have do we really have evidence that these effects on maternal and child health are real, and does that vary across the different maternal and child health outcomes? Might the evidence for some outcomes be quite strong and others much weaker? So this term sensitivity analysis is also used to assess other forms of bias, like that due to measurement error or selection bias or model misspecification. I'll be focusing here on unmeasured confounding. We can potentially come back to some of these other forms of bias at the end if you're interested. The term sensitivity analysis, I think, is used more commonly in statistics and the social sciences and epidemiology. Sometimes we use the term bias analysis, but the idea is pretty similar. And an early application, and one of the earliest theoretical results for sensitivity analysis was application by Cornfield et al., who showed that the smoking lung cancer association was unlikely to be entirely explained by an unmeasured confounder, although there had been a number of studies during the 1950s that suggested a pretty strong association between smoking and lung cancer, sort of risk ratios of tenfold more likely to have lung cancer for smokers than non-smokers. There was a lot of skepticism that this was really causal, and rather famously, Sir Ronald Fisher had proposed that there was a genetic variant that was responsible for both smoking and lung cancer and might explain away the association. And so the approach that Cornfield and the co-authors took was as follows. Let's suppose we have a risk ratio estimate relating the exposure and the outcome, possibly having adjusted for some measured covariates. And in their work, they assumed that there was some binary unmeasured confounder, again, maybe a genetic variant, either present or absent, responsible for the association, and considered how strong the association between the unmeasured confounder and the exposure would have to be, and in some subsequent work, the unmeasured confounder and the outcome would have to be to completely explain away that observed risk ratio. If we let UA be the risk ratio relating the exposure and the unmeasured confounder, and UY that relating the unmeasured confounder and the outcome, then what they showed, and these are now sometimes referred to in epidemiology as the Cornfield conditions, what they showed is that you could not be entirely responsible for the exposure outcome association unless both UA and UY were greater than the observed risk ratio. So the relationship between both the exposure and the unmeasured confounder would have to be greater than that tenfold increase, and and that between the unmeasured confounder and the outcome would also have to be greater than the observed risk ratio, that tenfold increase. So that, in the context of smoking, that would require pretty substantial confounding. So here we have Sir Ronald Fisher happily smoking away. He had published in just a year before the Cornfield paper a letter in Nature in 1958 saying that he really thought that this Smoking Lung Cancer Association was due to some unmeasured genetic variant. There had been studies at the time suggesting risk ratios for the Smoking Lung Cancer Association as large as tenfold, one estimate, risk ratio of 10.7, confidence interval from 8 to 14, so pretty large effect. And so what Cornfield and co-authors showed was that for such an unmeasured confounder to explain away the association, the genetic variant would have to increase the likelihood of both lung cancer and be related to smoking by risk ratios of tenfold or more each to explain away the effect. At the time, that really didn't seem terribly plausible. And so this paper was actually quite influential in having the general biomedical community accept that this association probably really was in part causal, and to the report of the U.S. Surgeon General in 1964 that action needed to be taken to address smoking in the United States. So these Cornfield conditions, I think, can still be useful rules of thumb for assessing how strong unmeasured confounding would have to be to explain away an association. But often we want to do a little bit more than that. We also want to say, well, maybe we don't think we have confounding that strong, but we think these are risk ratios of 2 or threefold, and how would that affect our estimate? So if we want to establish a range of plausible estimates, then we turn to these sensitivity analysis techniques rather than using simply these Cornfield conditions. Okay. So I'll be going through now the technical work, almost an extension of these Cornfield conditions to much more general settings that published with Peng Ding in 2016. We have our exposure A, outcome Y, measured covariate C. Our estimate of the risk ratio, if we adjust only for C, is comparing the probability of the outcome amongst the exposed and the unexposed within strata of the covariates. Ideally, we'd want to adjust for some unmeasured covariate U. We don't have data on that. If we did adjust for U, if we could adjust for U, these would be the expression for the adjusted risk ratio. If we want to sort of interpret this within a potential outcomes or counterfactual framework, we can let YA be the potential outcome for each individual if contrary to fact A had been set to little a. Our causal risk ratio is then just comparing the probability of the potential outcome Y1 versus Y0 being 1, conditional on the covariates. And if the measured covariates C themselves suffice to control for confounding, then that first empirical expression would equal our causal effect. But if we needed U as well, then the second expression would equal, or second empirical expression would equal the true causal effect, but the first would be biased. And so what we're going to do is we're going to define a bias factor, which is a comparison of the ratio between our estimate, having adjusted only for the measured covariate C, and essentially the truth, what would have happened had we adjusted for U as well. And we'll provide an expression for this bias factor B, or we'll be able to bound this bias factor B with various sensitivity analysis parameters relating the unmeasured confounder to the exposure and the unmeasured confounder to the outcome. So that's sort of often the game in sensitivity analysis. There are different approaches, but a lot of it is express the difference between the estimate and the truth in terms of these sensitivity analysis parameters that we can perhaps more easily interpret. And there's quite a number of techniques to do this. There's sort of a large literature on this relating the bias factor to different sensitivity analysis parameters for the effect of the unmeasured confounder on the outcome and the relation between the unmeasured confounder and the exposure. And here we're doing it on the ratio scale, but lots of the techniques are also for a different scale. I'll come back to different scales a little bit later. Many of these techniques to get closed form expressions end up making assumptions. about the nature of the unmeasured confounder. So a very common assumption is that unmeasured confounder is binary, and that often makes the analysis much more tractable. So much of the earlier work, and even much of the contemporary work, assumes a binary unmeasured confounder. Another very common assumption, which again makes the analysis more tractable and leads to closed form expressions for sensitivity analysis, is that there's no interaction between the exposure and the unmeasured confounder on some scale, so that the effect of the unmeasured confounder itself on the outcome is similar for the exposed and the unexposed. Maybe the unmeasured confounder increases the outcome by threefold, but it's that same threefold increase for both the exposed and the unexposed. So that's another very common assumption. And then another assumption that almost all techniques make is we only have one unmeasured confounder. And so these sensitivity analysis techniques are sometimes criticized for making assumptions to assess assumptions. I mean, we're assuming that our measured covariate C have controlled for confounding. We're worried that that's violated by some unmeasured covariate U. We're trying to assess the robustness of our conclusions, but now we're making assumptions on the unmeasured confounder to be able to test our assumptions. So what do we really gain? So the sometimes criticized in that regard. I'm not fully sympathetic to those criticisms. I think most of the sensitivity analysis is really just trying to get a general handle on how sensitive or robust our conclusions are, rather than trying to provide precise, corrected estimates. But I've had these criticisms leveled in my own application of these sorts of techniques. So the original technical work that Peng and I did was really trying to address this criticism. Could we relax these assumptions? Dustin?
So I thought, in regards to the only one confounder, it was only it was up to a linear combination of potential confounders.
Yeah. No. So you could define a new unmeasured confounder.
So it's not just one confounder. It could be many confounders, but
they have to be linear. Linear comment. Yeah. No, that's right. And what happens if the associations are non-linear, if it depends on one quadratically? Again, I'm quite happy with all the previous techniques as well. I've used them, but sort of had these criticisms both when teaching the material, but then also when trying to apply it in empirical studies. There are some techniques that don't impose these assumptions, but generally the ones that don't impose the assumptions either require specification of a huge number of sensitivity analysis parameters. You have to start specifying the effect of the unmeasured confounder for each of the exposed and unexposed groups, and how that differs for each possible level of a multivariate confounder, and it becomes a mess. Or the techniques that also don't make these assumptions avoid any reference to an unmeasured confounder at all, and essentially just have you assess, do you think the extent of bias is larger than your effect estimate or not? And it's unclear that those are necessarily helpful in trying to develop intuition as to robustness of conclusions. So again, the original technical work was trying to relax these assumptions. We defined two parameters, and somewhat remarkably could still obtain closed form sharp bounds, which were often quite informative. So we've got two parameters essentially relating the unmeasured confounder to the outcome and the unmeasured confounder to the exposure. For the parameter relating the unmeasured confounder to the outcome, we look at the maximum effect comparing any two values of u. U could be categorical, it could be multivariate, but it's for whatever u is, compare the maximum effect you can have on the outcome on the risk ratio scale, comparing any two values of u for the unexposed, and then what's the maximum value effect of u on the outcome for the exposed, and then you take the maximum of those two. So we're sort of relaxing that no interaction assumption here. You might affect the exposed and the unexposed quite differently, but we're just taking the maximum of those two. And then the second parameter relates the exposure to the unmeasured confounder. It says for any two values of the unmeasured confounder, Maybe we have an unmeasured categorical unmeasured confounder with 7 levels, and we compare level 2 to 5, and we say how much more likely are the exposed and the unexposed to have that value of u be 5 versus anything else? How much more likely are the exposed and the unexposed to have the unmeasured confounder take the value 2 than anything else? And we take the maximum of those. So for any level of u, what's the maximum risk ratio relating the exposure to the that value of the unmeasured confounder. So if you were binary, this would just be a simple risk ratio relating the exposure to the unmeasured confounder, but we can define this more generally for any u. Importantly, these parameters are defined conditional on the measured covariate C, and I'll be coming back to this point. But essentially what these parameters therefore are picking up is the residual unmeasured confounding, having adjusted already for the unmeasured covariate. So maybe in the breastfeeding study we think, oh, we haven't adjusted for home ownership or the size of the house, and maybe that would be related to how easy it is to breastfeed and also to our various health outcomes, and so we're concerned about that. But if we've also adjusted for income and education and wealth and occupation, then what these parameters are picking up is the residual association between home ownership and breastfeeding and the outcome, having already adjusted for these other 4 covariates. So that often means that these parameters are in fact much lower than they would be if we hadn't been conditioning on the measured covariates. But we'll come back to that in the discussion. Okay, so what we showed then in this paper was that with the parameters thus defined, the maximum bias that could be generated by such an unmeasured confounder, once we've specified these 2 parameters, we might do 3 and 2, say, is given by this really simple formula here. The product of the 2 parameters divided by their sum minus 1. So pretty easy to implement if they were 3 and 2, if we thought that home ownership increased the likelihood of our, let's say, childhood leukemia outcome by 3-fold, and was twice as likely among breastfeeding mothers than non-breastfeeding mothers. We'd do 3 times 2 is 6, divided by 3 plus 2 minus 1 is 4. We'd get a factor of 1.5. And that would mean the most such an unmeasured confounder could alter our risk ratio estimates would be by a factor of 1.5. It is impossible for such an unmeasured confounder to bias our risk ratio more than that. And so we could get a corrected risk ratio estimate, a conservative risk ratio estimate, by just taking our observed risk ratio and dividing it by the bias factor. And we would know that that unmeasured confounder couldn't shift the risk ratio more than that. These bounds are sharp in the sense that we can always construct a U with the parameters that we've specified, which achieves that bias factor, which really does alter the effect that much. So a given unmeasured confounder might not affect the risk ratio estimate as large as the bias factor that we've calculated. It may be less than 1.5, but we can always construct a binary unmeasured confounder that will in fact shift the risk ratio by a factor of 1.5. Yep.
I was just gonna, so do you need some sort of assumptions, like a positivity style assumption? Because imagine the unmeasured confounder is just like a unit fixed effect. And then I basically say that there are some people in society that conditional on U are either probability 1 or probability 0 of having the outcome. Yeah. And so there you're just gonna have, like, this is gonna break down obviously in that limit. But even if you have things that are approaching that, yeah, I guess this becomes like very uninformative.
Yeah, so if that were the case, then this parameter would be infinite.
Yeah.
You do actually still get bounds, and what you recover are the cornfield conditions.
Okay.
So this is better than we'll see this is better than the cornfield conditions, provided neither of them are infinite. If one of them's infinite, then you get back the cornfield conditions. Sort of relatedly, and I've got some slides sort of in the appendix of this presentation. If you're willing to tolerate, let's say, up to 3% bias, and practice, we'd be pretty happy if we were within 3% of the truth. Then you could also define these parameters over any u that suffices to adjust the estimate to within 3% of the truth. So a coarsened confounder might suffice, and the same sort of techniques could then be applied. So that's more a point in the interpretation than the mechanics of this, but that's another way in which these results could still be useful, even if you were in a situation like the one you've described. Dustin.
So this is a conservative adjustment in part because you're taking the max across the sort of treatment and control conditions for the RRUI case,
Yep.
right? So, and that's fine, and I think intuitively when we're doing sensitivity analyses, we kind of want the conservative thing, but why not something else that's like taking like a weighted average across the two groups in terms of like the actual presence in the population, right? That would give you. That's different than the max operator, and it would give you a sort of like, yeah, there might be this like interaction between the treatment and the unobserved confounder, but I'm not willing to say I'm going to take the max of that. I'm just sort of take a sort of a weighted average of those two effects, and then that defines the RRUI.
Yeah, no, I think that's a good question. I think some of it depends on what the point of the sensitivity analysis is. So if what you're really interested in is kind of the best possible estimate given what you know, and you have some idea as to how large the confounding effects are, maybe even some idea as to how, if it's a binary confounder, how common it is, then I wouldn't recommend this approach. This approach is conservative. This approach is not making any assumptions. I would recommend other techniques. There's a host of them in the literature that really try to get more at the exact estimate. This is a conservative approach. As we'll see, it can be very informative. If, however, the context is not what's the best corrected estimate we can get, but how strong of an argument can we really make that this is causal, then I would argue that this approach really is very powerful because it's dropping all assumptions, and as you'll see, it's actually often quite informative.
What you're saying is this approach is more robust to reviewers.
I think this approach will be more robust to reviewers, and I'll make the argument here, and this is what I'll be very curious as to your response, I think will also be more attractive to not all, but most practitioners of our empirical statistical methods.
So just to go on Dustin's point, do you think we can use this approach to say if we accept 5% bias, what's the confidence interval of the estimates instead of just one weighted estimate?
Yeah. So I mean, if I've understood your question correctly, I'm not going into it in this presentation, but we can also do things like, well, my risk ratio estimate's 1.6. I don't really care if the true risk ratio is 1.03. I mean, that's a tiny effect. It has no significance. I want to know how robust is my conclusion that if I want to conclude that the risk ratio is at least 1.2. I've got an estimate of 1.6. I want to know how much confounding is needed to shift it to 1.2. I can do that as well. And the mechanics actually are pretty easy. You just take 1.6 divided by 1.2 and you apply the formulas that I'll be going through.
Is there a way to benchmark this against the stuff you can't measure? So how would I incorporate that?
Yeah, why don't I come back to that question? It will come up quite directly in the material that follows. Okay. So, I mean, what would happen if we return to that cornfield example and maybe Fisher responds, actually, I think there is a genetic variant which increases smoking and lung cancer by tenfold each. I think that's real. I think that's what's really the case. So if we specified our two sensitivity analysis parameters as tenfold each, and we plugged it in our bias factor formula, 10.7, 10.7, divided by 10.7 plus 10.7 minus 1, what we would get is a bias factor of 5.6, which still, in fact, couldn't explain away the effect. It would only reduce it to a risk ratio of twofold. And,
So what was Cornfield's result then?
so Cornfield's result was that each of these had to be at least 10
In order for what?
to explain it away. But it turned out Cornfield didn't do as well as he might have. We can do better than Cornfield. Cornfield said what he showed was for an unmeasured confounder to explain it away, each would have to be larger than 10.
But you're saying if that were the case,
It still wouldn't explain it
so
away.
he was wrong.
No, they do have to be at least larger than 10. It turns out they have to be larger than about 20. His statement was correct. It's just, it's sort of a one-way implication. Yeah.
But these are different, but your definitions of these risk ratios are the ones that you're going to use in the sensitivity analysis are different because they take this max operator.
If we move to the Cornfield setting of a single binary and measured confounder, they coincide exactly. So these conditions are definitions reduced to the Cornfield conditions for a single binary unmeasured confounder with no interaction.
Because this is what, like, when Dustin says it's conservative, it's only conservative if you adjust your thinking about the risk ratios, right? If your intuition about the risk ratios continues to be kind of what it is, and 10 means 10, then when you kind of use this new measure, like, because the maximums can be much, much, much different than the averages, right?
Yeah. But I mean, so what's remarkable here is we're making fewer assumptions than Cornfield. We are conservative, and we still do better.
Okay.
So again, I think the Cornfield conditions are helpful rules of thumb, but essentially what's going on is if you take our bias factor and you let one of the parameters go to infinity, what you recover are the Cornfield conditions. So where Cornfield, I wouldn't say went wrong, but where he didn't maximally use the information is he considered them one at a time. He considered the two parameters one at a time. If we consider them at the same time, we actually can't generate the sorts of biases of the magnitude that Cornfield might have thought possible. I mean, I don't know what Cornfield's psychology was. I don't know if he thought, well, if they were 10 each, then we really could explain this away. The result he showed was that they couldn't be explained away unless they were at least tenfold each. But that turned out not to be sufficient. Yeah.
I have another assumption for you to add, or a question about it. So there's sort of three unknowns. There's the relative risk that you care about. There's the AU effect and the it's UY and UA or whatever it is.
Yeah.
And I think a reasonable hypothesis is that, I mean, and the trick of this whole thing is, well, we don't know what RR is, and RR depends upon these other two things that we don't know. We never really thought about them before, but we can make assumptions about them, and we get this first one. So that's sort of the trick.
Yeah.
But in all likelihood, we know more about RR than we do about, right?
Yep.
We know more about the quantity of interest than we do
Yep.
about
Yep.
about relationships between unobserved variables and things that have never been studied.
Yep.
Really, right? So if you knew that we knew, let's say, we had twice as much uncertainty, just as a wild guess,
Yeah.
about the quantity of interest, how much more would we need to know? Could you incorporate that assumption, right? Because just to say, well, yeah, I mean.
Yeah, so I'll come back to that as a strategy for assessing
Okay.
some of these. But yeah, no, I think that can be a very helpful approach and practice. Let me just run through another two slides, and then I'll talk a little bit more about, I mean, what do we really do when we have data? All this is fine with this, smoking lung cancer example, but what would we recommend? Yep.
One more question. So could you go to the next slide?
The previous one? Or?
Yeah, this
Yeah.
one. The RR here is the sort of marginal effect, the overall effect, right? But the RRU1 and RAU are defined as C-specific. So whether this taking the maximum overseas or.
Yeah, so I mean, in this actual application, this was before multivariate adjustment methods were commonly employed. So these are all not conditional on any covariates, but in principle, the game would be, you give me a conditional risk ratio, having adjusted for C. And then I'll specify some parameters also assuming adjustment's been made for C in the interpretation of those parameters, and then I'll get a corrected estimate for your adjusted risk ratio. So here in this application, there are no covariates, but that's the principle. Okay, so I mean, in terms of like use for sensitivity analysis, probably these, the risk ratios of 10 really are implausible. I mean, incidentally, we have found evidence for genetic variants that are related to smoking and lung cancer independently. So I mean, Fisher was, in some sense, correct, except that the risk ratios are like 1.3, not 10. So Cornfield was more correct. But we could specify whatever we want. We could specify twofold increase in lung cancer, threefold increase for smoking, plug that in, get a bias factor of 1.5. We then divide the estimate and both limits of the confidence interval by 1.5 to get a corrected estimate and confidence interval. And this is essentially conservative. This is the most such an unmeasured confounder could affect the risk ratio estimate. We'd still have a large effect, even if we had pretty strong confounding here. But an objection to these sensitivity analysis approaches that's often put forward is like, we have, and I think this, you were getting at this, Gary, like, we have no idea what these things are. Like, what is UY? We don't have data on it. I mean, now we do as of sort of 2012, but that was 50 years later. So we have no idea what these things are. How do we do this? I mean, we could do we pull these numbers out of thin air? And so sometimes the objection to sensitivity analysis is leveled that there's too much subjectivity in sensitivity analysis to make it useful. We're kind of pulling numbers out of the air, and if the investigator wants, they could just choose two numbers to make their effect estimate look good, and then what have we really gained? And I think it's a reasonable objection and one that needs to be taken seriously, but I think there are a variety of different approaches that can more objectively ground sensitivity analysis. One, and this is the one I'll really be talking about for the remainder of the presentation, this is the one that's going to concern the E-value, is simply report how large the effects of the confounder would have to be on the exposure and on the unmeasured confounder to explain away the effect estimate, and to shift the confidence interval to sort of include the null. Those would be two separate numbers. But then you're not sort of choosing the parameters to make the effect estimate look good. You're just saying, here's how large they need to be to completely get rid of it. And that can be quite informative. A second approach, and sort of this is what I had been previously advocating, which none of my epidemiology students seem to ever take up, would be to create a big table of values for the two or however many parameters you have, the effect of the unmeasured confounder and the outcome on sort of one axis, the effect of the unmeasured confounder and the exposure on the other, and then a whole table of corrected estimates, and sort of let the reader decide what they think is plausible. If most of the table seems the effect estimate seems fairly robust, then you've got a lot of evidence. If just a little bit of unmeasured confounding would have sufficed to explain it away, then you think, well, we probably shouldn't draw conclusions. But very few people would ever seem to do this. A third approach, which I think can often be quite informative, is go through the measured confounders one by one, omit them one by one. So in each case, if you have k unmeasured confounders, just adjust for k minus 1, and see which of the measured confounders makes the biggest difference. Then ask the question, sort of, if an unmeasured confounder were as important as my most important measured confounder, would this suffice to explain away the effect? And that can sometimes be a fairly persuasive argument. How persuasive, of course, depends on how good the initial set of measured confounders really was. If we've kind of controlled for everything under the sun, it might be quite convincing. If we've only controlled for one or two covariates, it might not be convincing at all. But in certain contexts, I think that approach can be quite helpful. And then lastly, one can try to use external data or expert opinion to inform sensitivity analysis parameters. But here in the remainder of this talk, for this E-value, I'm really going to be focusing on this first approach, how much unmeasured confounding is needed to explain away the point estimate, how much unmeasured confounding is needed to shift the confidence interval to include the
I
null.
think 3 is a great idea.
Yeah, so 3 is
I
always,
think-
no, 3
Yep.
is, I mean, 3, sorry.
Do we think 3 is a good idea?
I thought 3
Yeah.
is what we do.
Yeah, I mean, I of course also do 1, right, because you can do it.
Yeah,
Yeah.
yeah.
But, like, it's just changing the question in a trick way, right?
Yeah.
2, letting the reader decide. We all do that, right? We're gonna do Bayesian analysis. You, the reader, are gonna choose theta sub 12.
Yeah.
You know what? The reader never knows theta sub 12.
Yeah.
Same thing with expert opinion.
Yeah,
Experts,
I
they are
agree.
the experts. They don't know no one else knows anything.
Yeah.
This is our problem. But 3 is an interesting idea, because basically what you're saying is that you're taking the sum total of what this literature knows. Like in political science, we control for party ID and education and ideology. And in public health, you control for prior health status and age and education, right? Those are the biggest confounders.
Yep.
And they might not be, they may be bigger confounders, but that would implicate the whole history of the literature. So in some sense, you have a
Yeah,
leg to
yeah,
stand
no,
on
no.
there.
So I think 3 is a good approach.
Yeah.
And I would be sort of in favor of using 3 and supplementing it with 1. I think the danger with 3 can be is that it looks better when you adjust for less.
Yeah, sure.
And so that sort of provides perverse incentives to say, well, this measured confounder is pretty important, but if I actually eliminate it and don't even tell people that I have it, and I mean, this perverse incentive actually comes up in a couple of papers in the econometrics literature, where the measure they report is by what factor would the unmeasured confounders have to exceed the difference that the measured confounders made to explain this away. The problem with that is that sort of the more you adjust for, the better job you do control for confounding, it looks like it's more and more sensitive to unmeasured confounding, which is completely the wrong conclusion. So when done honestly and well, I do think 3 is very useful. I've used it as well and will continue to do so, but there are some limitations. I think using 1, as we'll see, but then using 3 to try to get some handle on whether an unmeasured confounder of this magnitude is plausible or not is actually a very good approach.
But it seems like the way you would, so I agree with what Gary said, and just rhetorically speaking in seminars when I have done 3, being able to say,
Yeah.
you mean that has more of an impact than GDP or
Yeah,
something
yeah,
like that,
yeah.
it's very effective.
Yeah.
The addendum that I would add to 3 that I wonder if it would address your criticism is that that you would want to couple your reporting of, I've adjusted for these C's, well, like how much of the variance in the model did that explain? Right,
Yeah.
and so that then counteracts that incentives to only have a couple
Yeah.
small
Yeah.
C's, because you also have to report the fact that those C's didn't really even matter. In
Yeah.
which case, then what are you doing? You should probably also include some other things. And so, as long as you're incentivizing people to then include those additional things, then that gets you out of the
Yeah,
trap.
yeah,
that you
yeah.
mentioned.
No, I agree. I think that would be good. Yes.
You know the literature for publication bias?
Some of it.
So Chris and I just showed a paper, so the special issue on publication bias by the Journal of Quantitative Criminology. So there's a lot of parallel with the approaches you proposed here. So we did a literature review of all the existing methods in publication bias. So your number 1 is the number of file drawer approach in publication bias. And number 2 is my method with Chris. So we had like a revised T-score based on if you accept 10% publication bias or 20% publication bias. And then number 3, it's like there's a lot of
Parallels,
So
yeah.
I think it's good to have a repertoire of all these approaches, and then which one you use depends on what's your question, like what do you want to do in the specific sensitivity analysis.
Yeah.
So I feel like it's really nice to have this as a parallel.
Yeah, no, and I think all of these can be useful in different contexts. I mean, I think even 4 can be useful if you're really trying to do the best job possible at getting a corrected estimate. Yeah, we're guessing, but at least we're guessing amongst those who seem to know something. But these same approaches, I think, are useful in measurement error selection bias, publication bias. I think they're quite general. My principal aim in this, and really this will be the rest of the talk, is simply to try to get people to do something. And as I've thought through this, I'm optimistic that this approach of one, using the sort of simple implication of the results I've already presented, might be the most straightforward way to make something very common practice. And so that brings me to this new metric, the E-value. So the E-value is the minimum strength of association on the risk ratio scale that an unmeasured confounder would have to have with both the exposure and the outcome, conditional on the measured covariates, to fully explain away the exposure outcome association. It's essentially just doing that approach number 1, but using the results that aren't imposing any assumptions on the structure of the unmeasured confounder. So the E-value comes from the fact that it's a measure pertaining to the evidence for causality. And it's straightforward. It's sort of simply a solution to a quadratic equation to show from the Price bias factor results that the E-value is given by this formula here. Very straightforward to calculate. The observed risk ratio plus the square root of the observed risk ratio times the observed risk ratio minus 1. So one can make the claim if both of the sensitivity analysis parameters are greater than this E-value calculated here, then that could suffice to shift the estimate, but weaker confounding absolutely could not. So it's very, very simple to calculate. We sort of just plug in our point estimate, and we calculate it, and then we plug in the limit of the confidence interval closest to the null and calculate it again. And the argument is that sort of those two numbers really would be highly informative for assessing robustness to unmeasured confounding. So if we did this for that estimate of the relationship between smoking and lung cancer, we had a risk ratio of 10.7, plug 10.7 in, what we get for the E-value of the estimate is 20.9. And if we do it for the lower limit of the confidence interval, 8.0 plus square root of 8.0 times 7, we get 15.5. And then we can start making statements like, and again, these can be included even in the biomedical literature where we have no space to write anything. We can include sort of one simple sentence with an observed risk ratio of 10.7 and unmeasured confounder that was associated with both the outcome and the exposure by a risk ratio of 20.9-fold each above and beyond the measured confounders could explain away the estimate, but weaker confounding could not. And to explain away the confidence interval of an unmeasured confounder that was associated with both the exposure and the outcome by factors of 15.5-fold each, above and beyond the measured covariates, could shift the confidence interval to include the null, but weaker confounding could not.
Sorry for a very naive question. So nobody in political science uses risk ratios. Can you translate this to changes in the probability scale directly?
Not really. Yeah. So unfortunately, not really. It turns out, so I will come to how this idea can be applied if we have continuous outcomes or if we want to report things on a different scale. But it turns out that if what we do need to retain is that the definition of the sensitivity analysis parameters are themselves on the risk ratio scale. Once you drop that, if you move to a different scale, the results actually depend on the number of categories of the unmeasured confounder itself, which is terrible, and the bounds completely deteriorate as those categories increase.
I mean, maybe we can start using risk ratios. I mean, that's
my argument's only for the sensitivity analysis parameters. For other purposes, use the risk differences or differences in continuous outcomes or ratios of expected values, whatever you want, and I'll go through how to do this with any scale. But the E-value is always going to be defined itself on the ratio scale.
So will the E-value make any assumptions about the functional form of how U is dependent on Y and the observed covariates, or is it completely independent?
Yeah, completely independent. Yeah.
So I'm trying to think about like the underlying U. So you're not okay. So I'm trying to figure out. So there's a difference between thinking that, let's say, like using party ID as an example, right? So we might have a binary underlying U, which is Republican Democrat, and that's going to have a very different risk ratio, the way you've defined it, as with if I use a 7-point scale, and then I'm probably going to be comparing strong Republicans to strong Democrats. And the two risk ratios that would imply are very different.
Yeah.
And I don't know, for me as an end user or as a teacher of this, which of those two risk ratios is the one that 20.9 refers to?
Yeah.
Is it the worst of the two? Is it?
So this applies to any unmeasured confounder, which you think, or any set of unmeasured confounders, which you think is sufficient.
So I just need to
you
find
could
one.
take the minimum. You need to find, if you can find one where you think, if I adjusted for this, I'd get close enough to the causal effect, and you can find one where it doesn't exceed these thresholds, then you have evidence for causality. Because these bounds apply to every unmeasured confounder that you think would be sufficient to adjust for the confounding you want.
But if I can find one that exceeds that.
No, that's yeah. The implication is that if you can find one that doesn't exceed it, then you can't explain it away. You can't explain away the causal effect, because these bounds need to hold for any u. Yeah, for any u that suffice to control for confounding. That's the key. So you had a binary 1 and a 7.1, right?
You just said it the wrong. You had to have said it the wrong way.
No.
Because I have a variable that's a constant that never satisfies
But
that.
do you think adjusting for the constant will control for confounding?
No, you
So
just said-
that's
you just said
the-
You just said if I have a whole set of potential confounders, and I can satisfy this equation in any one of them, I'm okay.
No. So, but that whatever you put forward to me, you have to think is sufficient to adjust for confounding.
Oh, the set, you mean?
Yeah. So, I think your example was you had a binary 1 and a 7.1.
Right.
Okay, and maybe the risk ratio for the 7.1 is a 20-fold, and for the binary 1 it's only a 4-fold. Okay.
Right.
If you think that adjusting for the binary 1 would be sufficient,
Right. Okay. So that's
Then that's
so
fine.
that's like the key difference. So
Yeah.
That's what I was missing. So you need to come up with something that actually. So that's. I mean, I guess that's the thing that I'm having a hard time with, which is like, what is, for a lot of things,
Yeah.
at least in the social sciences, we think that there's like an individual level effect. And so then essentially what I'm doing is I'm just saying I want to take the range. I'm going to take the like, if I think that the unmeasured confounder is just something about the person, then essentially I have to say like the highest probability and the lowest probability, conditional on covariance, obviously, and compare those two.
Yeah.
And that seems like it's going to be really big.
yeah. So, and this is where the approximate results
Yeah.
become useful, where you can say, here are 3 ways of coding this unmeasured confounder, and I actually think any of the 3 will suffice to get me within 5% of the truth. If that's the case, then each of the 3 has to satisfy these bounds to explain it away. You might think, my binary one's not going to do perfectly. It will get me within 5%. I'm content with that, and I don't think the risk ratio there is more than 4.
Right.
And then you really do have evidence that couldn't explain it away.
And I guess like the slight unease about this is that but we don't study risk ratio, so it's not intuitive for us at all. But even more so, I feel like the risk ratio usually is not it's comparing two adjacent categories rather than going from the
extreme.
max,
Yeah.
right? So
Yeah.
that seems like some. So to say that unmeasured confounder that is associated with both the outcome and exposure ratio by 20.9-fold is slightly
Yeah.
not misleading.
Yeah.
Per se, but
It's imprecise.
yeah, it's hard
Yeah.
to
Yeah.
yeah. You need the word counts increase.
Yeah.
So.
Chris.
I understand what you're saying. I wonder if you give us intuition. So if one of these, its value is just a little below your E value, and the other one is like wildly higher than E value, the unobserved confounder cannot explain away.
No, that's not the case.
Okay.
Yep.
That's right.
If one of them's a little bit below the E value, the other one would have to be considerably above. So the statement is that with this observed risk ratio and unmeasured confounder, which is associated with each by risk ratios of 20.9-fold each above and beyond the measured confounders, could explain away the point estimate. It is possible to construct a scenario
This is sufficient.
which it
That's
could,
unnecessary.
but weaker confounding could not, where confounding the strength of confounding is defined by that bias factor expression.
There are two implications. One implication is that if both are greater than 20.9, then the effect is neutralized. But the other
Or could,
implication-
again, could be neutralized because these are conservative. Yeah.
That's sufficient condition. But the other implication is that at least one of the confounding correlations has to be greater than 20.9.
That's right. Yeah.
That's a necessary condition.
Yeah. So, if you wanted to explore that, the next slide, you could sort of instead present a picture where you plot the two bias factors and you say, here is the values of the two sensitivity analysis parameters that would suffice to explain away the effect estimate, and we'd need the two to be in this region here. Here are the values of the two sensitivity analysis parameters that would suffice to explain away the confidence interval. We would need something in this region here. So we could do, a little bit less than 20. We could go down to 15 with the relation with the exposure, but then we'd need something like 35 for the outcome. So you could do a diagram like this if you preferred. Again, the goal was simply to provide something that was easy to calculate and that I could provide simple text for my epidemiologist colleagues to sort of report in one sentence in the results section, which would still be informative. That was sort of the goal of this. But we have software which will give you the fuller plots. Or if you think you know the parameters, you can do that too. And I think an approach like this can be useful going across outcomes, especially for the same exposure when study designs are similar. So here are some data for maternal breastfeeding and associations with lower respiratory tract infection of the child, subsequently maternal ovarian cancer of the mother, childhood leukemia. Here are the risk ratio estimates, confidence intervals. All these have highly statistically significant p-values, sort of 0.0005, 0.0001, and so on. But the e-values are different. I mean, if we start with lower respiratory tract infection, estimate 0.28, confidence interval 1.4 to 0.54. Oh, I forgot to mention, if you have a protective association, then you take the inverse before applying the formula. So if we have 0.28, we take the inverse of 0.28, that's 3.57, and then we plug it into that easy formula. We get an e-value of 6.6. We do that for the lower limit of the confidence interval, the limit of the confidence interval closest to the null, 0.54, take the inverse, plug it in, e-value for the confidence interval of 3.1. Pretty substantial confounding here would be required to explain these things away. We don't, again, this is always going to be context specific, but we don't get risk ratios of sort of 6.6 or even 3 very often. And for something to be associated with both the exposure and the unmeasured confounder by and the outcome by threefold each above and beyond the measured covariates would I think strike most epidemiologists as fairly implausible.
So I'm still on this track of thinking through how you convince everyone to do this, right? So it strikes me one way is, all of this is playing the game of sensitivity where we want to see, if my results are going to go away.
Yep.
But the other side of confounding is I adjust for, there could be an unobserved confounder that were I to adjust for it, my results would get better.
Yep.
Right? And so it seems like you could have sort of two versions of this.
Yep.
This is how weak your results might be,
Yep.
but by the same token, by the same symmetry that it is unobserved and hence ex ante, we don't know
Yep.
that might make your results better. People would get even
Yeah.
stronger results.
Yeah, so we go through this in the paper. You can do the same thing. I mean, sometimes in the biomedical literature, people say, well, we've got this observational data, and look, this drug looks safe. There's no side effects, but you could ask, well, how much unmeasured confounding would be needed to shift your risk ratio estimate from 0.05, which looks fine, to 1.3, where you might be concerned, and you can report that as well. So that's right. Yeah.
Do you have an R package already? If you do,
Yeah.
I'll be very inclined to use your method.
We have an R package. We even have a online calculator website now. So I think this group's quite happy with using an R package. Some of the clinician colleagues we work with have never even heard of R, and so you can just go to the website, you select your effect measure, whether it's a risk ratio or a difference in continuous outcomes or a risk difference, and you put in the confidence interval, and voila, you get the e-value for the estimate in the confidence interval. But we do have an R package. The R package will also give you the plots and so on if you want.
What's it called?
E-value. So I have the...
How do you do it for the risk, for the difference in, what did you call it?
We'll get there. We'll get there if I can go on. Yes.
It's more about, sorry, so is how you would put, so on that plot, another way you kind of classify it is you put basically the things you actually control for on the plot in the same scale, and then look whether, anything we've controlled for is above this sort of threshold. Is that something you could do?
Yeah, you
better
could.
as
I mean,
well?
our software doesn't, but yeah, that could be a nice feature to add. Yeah.
That gets at number 3.
That gets at number
And
3.
that's-
Yeah.
And that's how common, but you have one figure where you have
Yeah.
this sort of curve, and you just plot everything you control for. You could say, if anything we controlled for
Yeah.
above this thing we're worried about, and that's
Yeah.
one
No,
figure
that would be a
makes
nice addition to the plot. I will raise that with the graduate student who put that together. It would be nice to do.
But when you get a really large risk ratio, the e-value would be basically twice that, right?
Yeah, that's right. So the e-value, as the risk ratio gets larger and larger, the e-value converges to twice the risk ratio estimate. But it's highly nonlinear for small risk ratios. So, and sort of the critical areas, the transformation is in fact not straightforward. It's obvious, it's easy to calculate, but it's very difficult to do in one's head or to develop that intuition. So anyway, if we did this for all 3 examples, we could get e-values for the estimate, e-values for the limit of the confidence interval closest to the null. We'd have pretty substantial evidence here for lower respiratory tract infection, moderate evidence for maternal ovarian cancer, but kind of more modest. I mean, some evidence, but more modest for childhood leukemia. So, I mean, if I were, in light of these results, to sort of asked to place bets with lower respiratory tract infection, I'd be quite happy to do so. With childhood leukemia, I'd be a little bit more cautious. But again, with all these sensitivity analysis techniques, you're not getting a single definitive answer. All you get is some measure of the robustness of conclusions. But I think it would be useful to report these e-values in addition to our estimate confidence intervals and p-values. I really think it would help with assessing the evidence for causality, and it's getting at something very different than the p-value. The p-value is a measure of evidence for association, whereas the e-value is a measure of evidence related to, is that association really causal? And the two can go in different directions. So, and that actually turns out to be the case here. If we look at the p-value for leukemia, which has a smaller estimate, it's actually more extreme. It's less than 0.0001. Whereas the p-value for maternal ovarian cancer, it's still fairly extreme, but 0.006. Not as extreme as leukemia, but the e-value for ovarian cancer is more extreme than it is for leukemia. So we have stronger evidence that there's really association for leukemia, but we have stronger evidence that association is causal for ovarian cancer. So I think it's worth reporting in addition to the p-values. And they have different properties. The p-value can always be made more extreme by increasing the sample size. The e-value cannot. It will sort of converge to the e-value for the true, actual confounded association. In a different context, with different parameters, Rosenbaum refers to that as the design sensitivity. What happens as the sample size goes to infinity? What does robustness to unmeasured confounding look like in that scenario? While I think those measures can be useful in some contexts, I think most of the time we care not about an infant sample, but our actual sample. How much evidence do we really have in our actual sample? And so again, I think these sorts of statements could very easily be inserted into text. So few additional important points on interpretation. First, this really is always context specific. What is and is not a large e-value depends on the measured covariates that have been controlled for. If you've controlled for everything under the sun, that changes the interpretation of those sensitivity analysis parameters because it's the residual unmeasured confounding that they're capturing beyond what we've already adjusted for. What's a large e-value is also relative to the exposure and the outcome. So if I had an e-value of twofold and my outcome was mortality, I might think, well, we don't have many risk factors that increase or decrease mortality by twofold, kind of 30%, maybe sometimes 50%, but twofold, generally not. Whereas for suicide, if my outcome were suicide, twofold, we have got quite a few risk factors that increase the likelihood of suicide by twofold. So a lot of this really is context specific. As we've pointed out already, the e-value is conservative. It makes no assumptions about the structure of unmeasured confounding. So having sensitivity parameters equal to the e-value doesn't mean that the unmeasured confounder will explain it away. It simply means that it could. We can construct scenarios where it can. The implication of that is after we've controlled for these covariates, if we still have an effect estimate and we have a substantial e-value, we really do have strong evidence for causality, but it's much more difficult to make the argument that we have evidence for the absence of an effect. Again, sort of the absence of evidence is not evidence of absence. So where this metric's really most useful is trying to make arguments that are evidence for a causal effect really is quite substantial. Related to Dustin's question earlier, we can also calculate non-null e-values, how much confounding would be required to shift our estimate to any other value. That could be towards the null or it could be away from the null, but we can do this as well. The same approach works with odds ratios and hazards ratios with the rare outcome ratios of count outcomes. Continuous positive outcomes, if we take ratios of those, we just replace the risk ratios with the hazard ratios or the odds ratios. For odds ratios with a common outcome, those tend to vastly exaggerate risk ratios. And I've shown in some work recently that in many cases it's approximately actually the square of the odds ratio ends up being the square of the risk ratio. So as an approximate conversion to get from the odds ratio to the risk ratio, one can take the square root of the odds ratio. And it turns out that provided the outcome probabilities are between 0.2 and 0.8, that transformation will be within 25% of the risk ratio, whereas the odds ratio itself can be biased up to a factor of 400% for the risk ratio. So it's somewhat of a surprising little conversion. I've also been able to show its minimax for of any transformation. That's not yet published, but for any transformation of the odds ratio on the bias ratio scale. So the proposal, if you have fit a logistic regression with a common outcome, would be to take the square root of that odds ratio and the confidence interval, and then apply the e-value formula to get approximate e-values for the risk ratio. Question?
Thanks. If you go back one slide, please. Could you please help me understand why will it not explain away, but could explain it away? I didn't really get that.
Yeah. So, I mean, a classic example would be if you had an unmeasured confounder which had really strong effects on the exposure and the outcome, but was exceedingly rare. Maybe the prevalence in the population is only 0.001%. And so it's actually not going to generate much bias. These bias factor and e-value calculations are maximums over all possible scenarios. They're making no assumptions whatsoever on the structure of the unmeasured confounder. But like a really, really rare unmeasured confounder could have substantial sensitivity analysis parameters. Yeah. So again, these arguments are most useful when you want to say, I have real evidence for a causal effect. It's much harder to say, I really think that there is no effect at all, and I've got strong evidence for that. I mean, statements like that, I think, can generally only be made in very large randomized trials. Okay, what about continuous outcomes? Here, like with odds ratios for a common outcome, we can only get approximate e-values, but what we can do is essentially use the approaches that have been commonly used in the meta-analysis literature to convert a standardized effect size. So we take our outcome variable divided by its standard deviation, get a standard error for that, SD, and then we can get sort of approximate risk ratios, approximate odds ratios, and we can convert those to approximate risk ratios and calculate approximate e-values based on those. So this is what our software will do as well. There are other techniques for continuous outcomes as well. And I think they're perfectly good. I've used them. I'm not so concerned about the assumptions that are being made to derive the formula, but we thought for those who want to sort of standardize everything on this e-value metric, these approximate conversions could be useful. So again, our R package, the theories in the 2017 paper, but the R package and the online calculator will handle any of these scenarios. So the advantage of the e-value, it's easy to compute. One can do it by hand if you want, but we do have an online calculator on this website as well as an R package, which will do this automatically for all these effect sizes. It's easy to report and interpret. You can sort of add one sentence to the method section and one sentence to the results section, and you're done. It's sort of a standardized metric that can be used across different outcome scales. It can be calculated without making assumptions on the nature of the unmeasured confounder. It sort of was one approach to remove subjectivity in these sensitivity analysis metrics. And unlike a lot of the earlier results, it's also defining the parameters on the risk ratio scale rather than the odds ratio scale. And I've come to think that those sensitivity analysis parameters, like sort of the Rosenbaum-Rubin 83, and a lot of the ones in epidemiology as well, which define the parameters on the odds ratio scale, actually end up severely exaggerating the robustness, because odds ratio of 9 really only gives you a risk ratio of 3, and they're almost always interpreted as risk ratios. So I actually think there should be a move from the odds ratio scale to a risk ratio scale, because odds ratios are so commonly misinterpreted. When to avoid the e-value, I would say really shouldn't be using the e-value if you know what the unmeasured confounder is, and you know it's rare. I mean, in that case, these e-value calculations are so conservative. I would go to some of the techniques that force you to specify the prevalence, which is making an assumption again, and often they have to make a no interaction assumption, but I think they're going to be much more informative than these e-value calculations. So I would say this is one context. Maybe there are others as well, but I would say this is one context where the e-value approach really isn't all that useful. So in conclusion, I really do think, going back to the beginning, that some sort of sensitivity analysis for unmeasured confounding should pretty much always be used in any observational study intended to assess evidence for causality. I'm not saying you have to use this one, but I think something really should always be done. These techniques here have the advantage of not making assumptions about the structure of the unmeasured confounder, and so can potentially address reviewer techniques. It's pretty easy to calculate the minimum amount and report the minimum amount of unmeasured confounding, which would suffice to explain away the estimate or the confidence interval. And if the e-value suggests the evidence is robust, I think you have a very strong argument. I think the extreme skepticism, which one sometimes encounters in econometric circles of, well, no regression analysis could ever provide evidence for causality. We need a natural experiment. I really don't think it's true. I think if we have a well-designed longitudinal study with good confounding control, and these metrics are indicating strong robustness, I actually think that's a very strong argument. Again, it's much more difficult to provide an argument that the effect is absent, that you have no effect. But if you're trying to argue for evidence for the presence of effect, I think these e-value arguments in conjunction with a strong study design and good measured confounding control can be very powerful. And in general, I think with our observational research, too many practices have really been inherited from the randomized trial literature. I mean, our focus on the p-value is crazy, because often the central threat to our inferences from observational data is not statistical uncertainty, it is unmeasured confounding. And so while sort of giving the p-value the importance we do in randomized trials might be reasonable, we obviously have to take other things into account with regard to follow-up and fidelity of the intervention and so on. I think those practices are absolutely crazy for observational data, and I think the e-value was one way to try to correct this, report the e-value along with the p-value. I'm not suggesting we throw the p-value out, I'm just suggesting that we supplement it with another very straightforward metric to assess robustness. So I do think this approach could potentially be used very broadly. It's had considerable uptake already in the last 6 months in the biomedical literature. Again, I think because it's easy to compute, easy to report, and relatively easy to interpret as well. So my hope is that this at least provides one very straightforward way to try to make sensitivity analysis routine and common practice. So that concludes my presentation. Happy to take any questions. Thank you.
I think this is great. I think in a sense you presented a rhetorical paper, right? Or maybe even a haristhetical paper for my political science friends. So in that light, just 3 comments. First of all, odds ratios are stupid. No one understands how to report them. No one understands even what they mean. Even when they know how to calculate them, they don't know how to explain to actual human beings what they mean. I think it would be great if you actually said that. I've said that, but
no.
But if you said it, it might matter. In that field. 3 comments. Second is, I think you should call this this paper "Correlation Implies Causation."
That would have been better. Yes, I could only go back.
And third, you have by you, I mean you and your people have this way of reporting, this particular parenthetical phrase that your stuff that you always put in there, CI colon and all this stuff. I think you should tell people exactly what to do. Like, don't say put the calculation there. It should say CI colon, 95% colon, right, and then another semicolon or a comma or whatever it is you think is right. E-value equals. Tell them exactly what to do, and then they'll do it.
Yeah, I mean, in this paper in the Annals of Internal Medicine, we say, here is text that you can copy and paste into your paper. I mean, we've gone as far as that. What I should have done is I should have delayed publication until the software package was there as well. We provide some resources. It's not difficult to do by hand, but
you have to write a paper. You have to write. You have the math published, so now you have to write a paper for the people.
No, but that's what the 2017 Annals of Internal Medicine was. The 2016 paper had the math. The 2017 paper was using that math to say here's the e-value. But yeah, it was on your odds ratio point. It's a challenging one because I think so much of what we do is shaped by software, really, and we've got that great logistic regression package, and that's what clinicians use, and it is hard to get them to shift. No, certainly, and I mean that's what I do in sort of any time I'm working with a common outcome, we calculate risk ratios instead of odds ratios, but getting. I mean, there have been plenty of people who have written about this in epidemiology and the biomedical sciences, but getting practices to change is difficult. And I mean, this was what I was struggling with sensitivity analysis in general, and trying to do all this teaching and sort of came to, unless you have software and something really easy to do, it's not going to happen. So what we need to do is convince SAS to, whenever someone writes proc logistic, it calculates the probability of the outcome, and then if it's too high, it actually fits a different model. That would be the the solution, I think.
So on Gary's point, at the beginning of the talk, you said, how difficult it is to even get the students to use your method. So writing the paper with Chris makes me realize that a lot of it really depends on the journal editors. You know, like the editors could ask for replication packet, or like say you have to put this robustness check in the online supplement, even if you don't want to keep it in the main text. So like in politics, we have a conference of mayors, but like in this issue, can we have a conference of journal editors or like software designers, and then we sell them all these ideas of robustness checks and publication bias? Do you think that will transform the whole field?
Yeah, no, I think the practice of editors makes a huge difference as well. And half, I would say, of the uptake of the e-value thus far has been that if you submit anything to the Annals of Internal Medicine now and it's observational data, they'll force you to calculate an e-value. But I think it's when editorial practices change that it makes a difference. I mean, I will say I've had much more interest from student use. From student users with this than any of the sensitivity analysis stuff before. And again, I think it's because it's a single number and just kind of one line that they can insert in. I mean, while I think it's important to do our sophisticated methodologic work to address complex questions, I've also come to the perspective that the actual practice of biomedical or social science is it's a complicated sociological phenomenon, and a lot of it is what is easy to do and what's considered necessary to get something published. So I think those issues about editorial practice are very, very important.
That's all the time that we have today. If you have any questions, you can talk.
Yeah, I'm happy to stick around.
But thank you everyone for coming.
And you can download the paper or the online calculator or the R package from my website, should you so desire. Great.